Our universe is not static, it's in a constant state of expansion, stretching space itself in all directions. This ongoing inflation makes it incredibly difficult to measure its boundaries or estimate its actual size. At the center of this cosmic expansion lies a strange and invisible force known as dark energy, which is causing galaxies to move away from each other faster as time goes on. Scientists track this cosmic growth using a method called redshift, which observes how light from distant galaxies shifts toward longer wavelengths as they recede. The launch of the James Webb Space Telescope, JWST, has revolutionized our ability to observe this expansion. With its advanced infrared sensors, JWST can peer through cosmic dust and uncover ancient light that older telescopes missed. Before JWST, the Hubble Space Telescope was our primary window into the distant universe. Although groundbreaking for its time, Hubble's limited sensitivity to infrared light left parts of the cosmic puzzle unsolved. Now, stationed far beyond Earth's orbit at Lagrange Point 2, JWST captures deep and clear images, revealing galaxies that formed just 300 million years after the Big Bang, forcing scientists to rethink how early the universe began to take shape. Public scientists like Brian Cox and Neil deGrasse Tyson often emphasize the vastness of the universe. Cox once compared the known universe to a grain of sand on a never-ending shoreline. The observable universe, roughly 93 billion light-years across, is only what we can see, the light that has reached us since the universe began. Beyond that lies the unobservable universe, potentially infinite and forever hidden. Even within the observable part, scientists estimate there are about 2 trillion galaxies, each containing billions of stars. This staggering count comes from deep space images like the Hubble Deep Field, which captured thousands of galaxies in what looked like an empty patch of sky. These galaxies aren't scattered randomly, they're arranged in a cosmic web formed by gravity over billions of years. This vast network contains filaments, voids, and galaxy clusters shaped by invisible forces. To bring it closer to home, our solar system, though immense by human standards, is tiny in cosmic terms. For comparison, driving non-stop at 70 miles per hour, you'd circle Earth's equator in about 15 days, reach the Moon in around 5 months, and get to Mars in 63 years, assuming the closest approach. But this is nothing compared to interstellar distances. Voyager 1, launched in 1977, exited the solar system's influence in 2012. Even after traveling more than 14 billion miles, it still hasn't reached the Oort cloud, the icy boundary of our solar neighborhood. Reaching the nearest star system, Alpha Centauri, would take Voyager about 70,000 years. Even light, the fastest thing in the universe, takes 4.3 years to get there. Our Milky Way galaxy alone holds over 300 billion stars. It stretches across 100,000 light-years, and Earth sits roughly 26,000 light-years from the galactic center. At the core of our galaxy lies a monster, Sagittarius A*, a black hole over 4 million times more massive than the Sun. Nearby stars orbit it at extreme speeds, their paths distorted by immense gravity. Our solar system revolves around the galaxy once every 230 million years. Beyond the Milky Way lies our local group, a cluster of about 54 galaxies, including Andromeda, the largest among them. Andromeda is on a slow-motion collision course with the Milky Way, expected to merge with it in 4.5 billion years. Yet, everything we can see, stars, galaxies, gas, makes up less than 5% of the universe. The rest is hidden. Dark matter, which forms 27%, holds galaxies together with its gravitational pull. Dark energy, the remaining 68%, is pushing the universe apart. These mysterious elements dictate the past and future of the cosmos. Some parts of the universe, like the Boötes void, are massive empty regions spanning 330 million light-years, almost devoid of galaxies. Meanwhile, cosmic filaments, structures made of gas and dark matter, stretch for billions of light-years, connecting galaxy clusters. Formations like the Sloan Great Wall. Our universe is not still. It breathes. It stretches. It moves. Every second, space itself expands, pulling galaxies away from one another, dragging the very fabric of reality outward in all directions. This isn't just stars and planets drifting apart, it's the stretching of the cosmic stage itself, the invisible scaffolding of existence inflating on a scale beyond comprehension. This phenomenon, called cosmic expansion, has been accelerating for billions of years. And at its mysterious heart lies dark energy, a force we don't yet fully understand, yet one that governs the fate of everything we know. It doesn't pull, it pushes. Unlike gravity, which draws matter together, dark energy repels. And the more space expands, the more of this force there seems to be, fueling an ever faster expansion. But how do we know this? How do we, tiny beings on a small rock circling an average star, glimpse the behavior of an entire universe? We watch the light. As galaxies move away from us, the light they emit stretches, shifting toward the red end of the spectrum. This is known as redshift, and it's the universe's way of revealing its motion. The farther away a galaxy is, the faster it recedes. It's a cosmic fingerprint of movement etched into ancient beams of light. The most powerful tool we now have to detect these faint whispers from the past is the James Webb Space Telescope. Orbiting far from Earth, positioned at Lagrange point 2, JWST avoids our planet's light and heat. It stares deep into the cosmos using infrared vision, seeing light so stretched by distance and time that it has become invisible to the human eye. Before JWST, the Hubble Space Telescope opened our eyes. Its deep field images showed thousands of galaxies in seemingly empty patches of sky. But Hubble had limits. It struggled to peer through dense clouds of gas or see the earliest galaxies, whose light had shifted beyond its vision. With JWST, those limits are gone. In its first year alone, Webb revealed galaxies that formed just 300 million years after the Big Bang. That's like seeing the universe as a toddler. These discoveries are rewriting what we thought we knew about the timeline of cosmic evolution. Galaxies were forming faster, growing larger, and becoming more complex far earlier than anyone predicted. And yet, even the observable universe, the part whose light has reached us in 13.8 billion years, is just a bubble. A speck. According to astrophysicists like Brian Cox, if the observable universe were a single grain of sand, the entire universe might be a beach that stretches forever. Its true size could be infinite. And we may never see beyond our local horizon, no matter how far our instruments improve. Inside our cosmic bubble, scientists estimate there are about 2 trillion galaxies, each home to billions, sometimes trillions, of stars. This mind-boggling number comes from deep space surveys using Hubble, JWST, and other observatories. What looked like voids were actually teeming with distant ancient light. These galaxies are not scattered at random. They form a vast cosmic web, an intricate structure of filaments, clusters, and voids, all sculpted by gravity over billions of years. These strands are made not only of stars and gas, but also of dark matter, the invisible glue holding the universe together. Though we can't see it, dark matter makes up about 27% of the universe's total content. Without it, galaxies wouldn't exist. They'd fly apart, torn loose by their own motion. In contrast, ordinary matter, everything we can see and touch, makes up less than 5% of the cosmos. The rest? That elusive, accelerating force we call dark energy, making up 68%,